Hey everybody, in this video we're going to talk about the chain rule and do some examples. Over here I have the formula for the chain rule. dy dx equals dy dz times dz dx. And you always have a chain of variables here. So you have some y that depends on some z that depends on some x. And when that happens, in particular when you have composite functions, then you want to be using the chain rule. So let's do an example here with number 1. In number 1, notice that we can build a chain like this, y to z to x. We can build a chain by saying, hey, this inside function, I'm going to call that z. Z will be x cubed plus 3. That's my inside function, and we often use z for our inside function. That means our outside function is y equals z to the 7th. And you can just see, if you plug in that z in there, you get that function. Alright, time for the chain rule. In the chain rule, after you've figured out the two pieces or more in your chain, you differentiate each piece. So I need to differentiate z to the 7th. That's the power rule, 7z to the 6th. Times, I need to differentiate this, the dz dx. So I need to differentiate x cubed plus 3. That is 3x squared. Notice that the plus 3 goes away. The last thing you absolutely have to do is you have to plug back in for the z. So 7, z we define to be x cubed plus 3 times 3x squared. Oops, I forgot to put the 6 up there. Let's add that. Now, if you wish, sometimes you'll see this rewritten. You can put the numbers together. 21x squared times x cubed plus 3 to the 6th. Now, I'm going to just talk a little bit about doing this with blahs, because that's another way I like doing this. So I'm going to write this down over here on the side, the same problem with blah notation. In class, I'd even cover this up with my hand, and I'll probably show you that in class. But I've got blah to the 7th. The derivative of blah to the 7th is 7 blah, all this stuff stands for the blah, to the 6th, times the derivative of blah. So that is 3x squared. So the idea is I'm thinking of all this stuff here as blah. So it's blah to the 7th, there's the blah, there's the derivative, ddx of blah. If this works for you, great. If not, don't worry about it. I'm going to show you this method as well. Let's do this for number 2. Again, I need to build a chain. For your z, what you're always looking for is an inside function. Inside parentheses, or in this case, inside an exponent. So z equals 3x plus 4. And then once you've figured out your inside function, write your outside function, negative 2e to the z. So dy dx is dy dz dz dx. Or in other words, we take the derivatives of these two functions and multiply them together. The derivative of negative 2e to the z is negative 2e to the z times the derivative of 3x plus 4. That's a line, so the derivative is the slope. Again, you have to plug in what z is. So I'm doing that right now, times 3. And again, you might combine these two numbers and get negative 6e to the 3x plus 4. All right, doing this in terms of blah, let's put some parentheses down here since I've got a minus sign. what I say is I've got negative 2 e to the blah. The derivative of negative 2 e to the blah is negative 2 e to the blah. Yay for e. Times the derivative of blah. And you can see I'm going to get the exact same thing as what I have there. It's two different ways of carrying out the chain rule. And again, I want you to find a way that works for you. So if the first way works, great, use it. If the second way works, great, use it. Let's do number 3. Now, I'm going to do something before I take the derivative here. I'm going to rewrite this. I know that we could use the quotient rule in this, but the fact is we don't have to, and in fact it would take more work to do the quotient rule. The reason why we don't have to use the quotient rule is because we don't have a variable up here. So this is a lot easier to write as 5 times square root of x plus e squared to the negative 1 power. Makes it look a lot like number 1, in fact. And in fact, I'm going to do one more rewrite. 5 times x to the 1/2 plus e squared to the negative 1. Please note that I haven't taken any derivatives yet, okay? I'm not done with the problem. I'm just rewriting it. So now, if I talk about what my chain looks like, again, you want to find an inside function. That's your z. And again, good hints for z are things in parentheses, things in exponents, things in denominators, or things in parentheses. So we'll use what we have in parentheses here. Okay, that means I have to write down what my y is. All right, time for the chain rule. And again, all this means is I'm going to take those two derivatives that the derivatives of the two functions I just wrote down. So the derivative here is going to be negative 5 z to the negative 2 times this derivative, which will be 1/2 x to the negative 1/2 power. Note that e squared is a constant. It doesn't involve x, so we're done. Okay, well, not quite done. We're done with that derivative. We need to plug in for z. So negative 5 x to the 1/2 plus e squared to the negative 2 times 1/2 x to the negative 1/2. I'll make one comment here. Of course, there's a lot you can do to rewrite this. We can rewrite that x to the 1/2 with a square root. We can rewrite this as a fraction since we have a negative exponent, and that is a fraction. You can do all sorts of rewriting. I'm not going to require that right now. As long as we're talking about this material in Chapter 3, where our goals are finding the derivative, don't worry about simplification too much. I'm much more interested in making sure that you can follow these rules. Now, I could do this with blah as well, and it's the same sort of idea. The derivative of 5 blah to the negative 1 is negative 5 blah to the negative 2 times the derivative of blah. All right, so that's some coverage of the chain rule.